we're going to do mean value theorem. Mean value theorem is one of the 5 theorems. Sometimes it feels like we have a million theorems to memorize. It's one of the 5 theorems that you're going to be held accountable to on the AP exam. Should we go through the list of 5? Ready? Okay, number 1 is the intermediate value theorem. Remember what intermediate value theorem tells you? If there's a value here at A and a value here at B, you've got to go through all of them, assuming that the function is continuous, right? It's the one that helps us verify that there's going to be zeros of a function. If f of A is a negative value and f of B is a positive value, there has to be a 0 somewhere in the interval, assuming it's continuous, right? Okay. Number 2, the extreme value theorem, aka the maximum existence theorem, which I won't actually write down right now because we've spent way too much time talking about it over the last week or so, haven't we? Extreme value theorem, maximum existence theorem. We know when maxes and mins exist. Number 3 we're going to do today, it's called the mean value theorem. Number 4 is the fundamental theorem of calculus version 1. And number 5 is the fundamental theorem of calculus version 2. Those are the 5 theorems that you are very, very likely to be held accountable to on the AP exam. So there's not a million. There's 5. 5's okay, right? 5 is close to infinity, yes. 5 is way closer to infinity than 1 over x as x approaches infinity. You're right. Good point. All right. Mean value theorem makes more sense with pictures, but we're going to do it with symbols because you need to understand both. Mean value theorem basically says f needs to be differentiable, aka continuous. Continuous is one of those continuous is one of the prereqs for differentiable, right? So it's differentiable, which means it has to be continuous. The interval, there exists a number c such that the slope of the function at the curve is equal to, what is this thing that I'm putting a rectangle around? A really badly drawn rectangle. What is that thing? That is not the derivative. It's pre-derivative. Not pre-derivative in the sense that it existed before, but it's something that we practiced before we actually got to the derivative. It is the slope of what? It is the slope of the secant over the interval AB, which is defined as, let's go back to chapter 2, that's the average rate of change over the function, right? So here's what mean value theorem says. Assuming your function is differentiable, means you can take its derivative. Assuming your function is differentiable, then there has to be a value on the interval for which the average rate of change is equal to the instantaneous rate of change. I'll draw pictures and try to make that make more sense in just a minute. Okay? And, well, you've got a picture on your notes. Let's get to it. Okay. Here's another way of writing it. I don't know that it's as useful at this point, but someday down the road, maybe that will be more useful. Okay? Let's take a look at a picture. And it makes more sense when we draw a picture, right? There's our picture. Okay? All of the functions over the last week have looked like that one. This applies to any function. Okay? We've got an A value, a B value. There's our interval. We're cutting off the function there and there. The function is differentiable. Okay. Mean value theorem says it's an existence theorem. It guarantees the existence of a point that has the same slope as the secant line. There's going to be a tangent that is parallel to the secant, provided that the function is continuous. Differentiable is actually the better qualification. Okay? So whatever this slope is, average rate of change, slope triangle right there, average rate of change over the entire interval, and the point is that you see that those two segments are parallel. There's your average rate of change, and this is the slope of some tangent on that curve. Okay? Could it happen more than once? Yeah, depending on your function. It could happen more than once. You could have 2 or 3 of these things that have the same slope as the function. But what the mean value theorem guarantees is there's at least one. Should I give you an example of one that's got more than one? Or do you just believe me? Should we look at one? Here's a good one. Let's make this A and this B. Here's your slope of your... See, that's the average rate of change. How many places potentially do we have where we could have tangents that are parallel to that? Going to be one here, right? Going to be one here. Kind of eyeball it, can't you? Those are going to be parallel. Okay, so the point of today, understand what the mean value theorem is. You're starting to get a picture? What does it tell us about the function, and how are we going to use it? Okay. Yeah. One example, and most of the time we talk about examples of when the mean value theorem applies. Want to give you just a brief example, and this is kind of an easy one. But the key here is if it's not differentiable, the mean value theorem does not apply. Okay, let's take a simple rational function like 1 over x. So 1 over x looks like this. That's 1 over x, isn't it? Okay, let's take some interval on 1 over x. And I'm not gonna just do some interval. I'm gonna do a particular interval. Let's call this a and this b. Compare the slope of the secant, which I drew in blue. I'm kind of adding this example. Compare the slope of the secant, which I drew in blue, to the slope of the red curves. What do you notice? The slope of the blue line is always, it's a positive slope, right? But what do you notice about the red curve? The red curve is always decreasing. How do you know? Because the derivative is negative, the curve is falling, right? So there is no point, this is an MVT fail, except MV, not FT. MVT fail. Okay, because the slope of the secant is greater than 0, but on 1 over x, the derivative, f prime of x, is always less than 0. Okay, just a kind of an easy example of when the mean value theorem fails. And why does the mean value theorem fail here? It's not differentiable. At x equals 0, there is a discontinuity. Therefore, not differentiable. Now, I want to be careful here, because it's not saying, just because the MVT fails, it doesn't mean there will never be a point at which the slopes are the same. It just says that you can't guarantee that there's going to be a point where the slopes are the same. Okay? This one's a complete fail. There are some that are not differentiable that do happen to have the same slope as the average rate of change, but the mean value theorem is an existence theorem that says if it meets these conditions, you're guaranteed that scenario. Okay? Good so far. All right, let's apply it. If it's continuous on the interval and differentiable on the open interval, and I guess the reason those are separate is that the curve needs to exist on a closed interval. It needs to have particular endpoints. But the definition of differentiable has to mean, I don't want to get into this too much, but you have to approach the same slope as you approach from both sides. And if I'm looking at an endpoint, I don't know, like if I look at a function that looks like this, you can't define differentiability at those points because there's no point on the other side of it. Okay? It's a finite interval. All right, so here's what it looks like. Here's what we're going to do. Basically, what we're going to need to do is we're going to need to determine whether the MVT applies. Number 2, what point or what characteristics of a point does it guarantee? And sometimes we're going to be asked to find the point that it guarantees. Not always, but sometimes you're going to be asked to find the point at which it is guaranteed. More often than, I mean, in a lot of the real-world examples, you're not necessarily going to need to find it, but I want to walk through one that shows you how to do it anyway. Okay? So let's look at example 1. Let's look at g of x. Quick show of hands. Yay or nay? We'll go yay first. How many think mean value theorem applies here? Raise a hand if you think it applies. Okay, I got 4 hands. 5, 6, 7, 8, 9. Okay, tell me why you think it applies. It's continuous. It's a cubic function. It's a cubic function. It's smooth. It's continuous. It's differentiable. Okay, polynomial functions are differentiable. So we're going to go ahead and say yes, because it's continuous and there's no sharp corners. Do you need to include the justification? I don't think so. I think stating it is enough. Stating it that you're acknowledging that it's continuous, you're acknowledging that it's differentiable. I don't think you need to defend that it's differentiable. Okay? What point does it guarantee? And this is kind of the this is the skill of it, and it's not an incredibly hard skill because it's an algebra 1 skill with some weird notation. The point that it guarantees is the slope of the secant. How do I find the slope of the secant? Go back to the algebraic definition of slope rather than the calculus definition of slope. Okay. It's not f, it's g. So let's do g. G of 1 minus g of negative 1, all divided by 1 minus negative 1, right? Okay. This fraction just finds the average rate of change. G of 1 is 1 plus 1 is 2, 2 cubed is 8. G of negative 1 plus 1 is 0, 0 cubed is 0. 1 minus negative 1 is 2. Okay? So we found that the slope of the secant is 4. So we determined the mean value theorem applies. We determined that the slope of secant is 4. So I think this is where you need to make a statement. I think you need to make a statement here that says there exists a c value on the interval AB such that f prime of c equals there exists a c, some c value on the interval from A to B. I'm just introducing a new constant on AB, such that f prime of c equals what? 4. That's it. That's not really challenging, is it? Okay. Question? Mm-hmm. Good question. When I found 4, I have answered question 2. I've guaranteed that a point, I don't know which point it is, but I've guaranteed that there's some point on the interval between these 2 points. So somewhere between negative 1 and positive 1, I have guaranteed a point that has a slope of 4. Okay? Well, yeah, I'm going to go ahead and find it. I'll do it for this one. I won't do it for all of them, but I'll go ahead and find it. I'm going to slide down and use some of the space down over here. I want f prime to be 4. So what a question before I move on. Sorry, g prime, thank you. Get my pronouns screwed up. G prime of c equals 4. Thanks for the clarification. Good. All right, so let's do g prime. What's g prime of x? It's a chain rule, power rule problem, isn't it? 3 quantity x plus 1 to the second times 1. So I'm not going to write the times 1. Okay? If g prime of x is going to be 4, let's set g prime of x equal to 4. Divide by 3, get x plus 1 squared equals 4/3. This is not going to be a particularly nice answer, but all I do is care that it exists, right? Whether or not it's nice is somebody else's problem. X plus 1 is then equal to plus or minus the square root of 4/3. And the x values, this one actually happens to have 2. -1 plus the square root of 4/3, and -1 minus the square root of 4/3. Those are the two x values that have a slope of 4. Okay. All we did was symbolic stuff. Mr. Best, you said earlier that it always gets better with a picture. So let's take a look at a picture. The function was x plus 1 to the third. You know what that looks like? It's this cubic function moved left 1, isn't it? We've actually, because we said the interval was from -1 to 1, didn't we? So we've cut it off here and here. The average rate of change is represented by, that's not very good at all. The average rate of change, weird that it did it that way. Average rate of change is represented by, just in a different color. Average rate of change is represented by this. Right? What's the slope of that red line? 4. And the mean value theorem has guaranteed that there's going to be some tangent on the curve. It's probably somewhere in here that is parallel to that. It's really all we've guaranteed by MVT. Okay? We found 2 of them. The other one was down here. The other one was not within our interval. Doesn't look very good. You kind of get what I mean though, right? There's another point down here that has the same slope, but it's not within the interval. Okay? I don't think you're going to be tricked like that, but it's worth looking at. But that one has 2. Okay? Good so far. Okay? Example 2. Does MVT apply? A couple of you said no. You got to convince somebody near you. Convince somebody near you that MVT does not apply. Why not? It's not continuous where? It's discontinuous. There is a discontinuity at x equals 3. Okay? Does that mean that there isn't going to be a point that has the same slope as the secant? It doesn't mean there's not going to be a point there. It just doesn't guarantee that there's going to be a point. Okay? So at this point, we'll stop there. There's a discontinuity at x equals 3. The mean value theorem does not apply. Right? Good? Stop there. Do I need to, if the point doesn't exist, there's no reason to go find it. Another question? Yep. What are you looking for to check whether or not it applies? You're looking for continuity, and you're looking for no sharp corners. So the idea would be, does that answer your question or not? Okay, you're given a function. Are you looking for point C? At this point, most of the questions involve, you're really going to mentally have to answer the question, is it continuous and does it not have any sharp corners? Then you're looking for the slope of the secant, which is then guaranteed to be a point. It's guaranteed to be a point on the function that has that same slope on the interval. Right. We're really, I mean, your question is valid. Once we know that it applies, number 2, you're really finding the slope of the secant on the entire interval, the average rate of change over the entire interval. And at this point, all we can do is we can state that it had to be. Okay, we'll talk about kind of the the speeding example. Okay, if we've gone a certain amount of distance, like if your average rate of change, if you're driving your car and the average rate of change is 65 miles an hour, there is a point where you had to have been going 65 miles an hour. That's just a kind of a real life example. You can't go 65 miles an hour on an entire interval without at least going that fast once. Yep. Good. We found that the slope at some point is 4, because if we draw that, I'll go back to this picture. If we draw the secant between -1 and +1, that slope was 4. The third step is really to find the point at which the secant is parallel to the tangent. And sometimes it's going to ask you to do that, sometimes it's not. We said the MVT guaranteed that f prime of some point C is 4. Actually, it was a G. Doesn't matter that much, but it was a G. And we said that G prime was this thing. And if we set that equal to 4, this is the slope of the secant. This is G prime. Those two have to be the same, and we're algebraically finding for what x value it's true. We don't necessarily need to plug it back in. If you plugged it back into the original function, you would get the ordered pair, but you don't necessarily need to do that. Pretty rare that you have to actually find that, especially with values like we got -1 plus or minus the square root of 4/3. You're probably not going to need to evaluate that. Okay. Okay, let's do one more. We're going to do example 3 or example 4. They're both the same, aren't they? Let's do example 3. Okay. Number 1. What do you know about the cube root of x? Is it continuous? It is continuous. Looks like that, doesn't it? On -3 to +3, something like that. Okay. Is it differentiable? You sure? Is it differentiable? Help me out. Where? Does the vertical tangent disqualify it from being differentiable? Does it? What? Does it? Does it? I think it's a valid question. That's an infinity symbol. What do you mean, is that a fish? That's a fish. It's got an extra tail. You don't have to close the fin. It's got a linear, so can you want me to do this? There. It's a fish. All right, so the question we need to clear up here is, does a vertical tangent disqualify it from being differentiable? And the answer is yes. And here's how you know. The question is, how do you know? What you need to look at in this context is you need to look at f prime of x. f prime of x, in this case, since f was x to the 1/3, f prime of x is 1/3 x to the -2/3, which looks like, if we put it back in terms of a radical, 3 times the cube root of x squared. Okay. As soon as we have a variable in our denominator, we know that there is a discontinuity on f prime. And that discontinuity occurs at x equals 0. And since x equals 0 is on the interval we're talking about, we are not guaranteed a point that has the same slope as the secant. Now, if you look at the picture we drew. Is there likely to be a point on that curve that has the same slope? Probably. But the mean value theorem fails because there's a discontinuity on f prime. There's a place where the derivative does not exist, which means at x equals 0, f is not differentiable. And the reason that this last example is on here is because on example 4, same function, different interval, this one, the MVT actually does apply. And if you look carefully at the notation, and I'm hoping not to trick you on this, but MVT applies, number one, because f is continuous, that's a lot of U's, continuous on the closed interval, right? Just like up here, f was continuous on the closed interval. It is continuous there, right? We drew it. That's continuous. Okay? This one failed because it's not differentiable. This one, the differentiability applies on the open interval. And I gotta make that a parenthesis. I don't mean to trick you on this, but the differentiability failure occurred at x equals 0, and that's not on the open interval from 0 to 1. I know that's a little weird, but MVT applies for example 4, but doesn't apply for example 3, even though it's the same function, and even though there's a good chance that we do have tangent lines that are parallel to the secant line. Does that help a little? Okay. I don't think you should worry about being tricked by this, but it is an important distinction. Okay? So, let's find the slope of the secant on the interval from 0 to 1. We want f of 1 minus f of 0, all divided by 1 minus 0. Okay? What's the cube root of 1? Cube root of 1? 1. Cube root of 0? 0. Over 1 minus 0, that's 1. So what we've done is we've guaranteed ourselves a place on the interval from 0 to 1 for which the slope is 1. Okay? Let's wrap up. Gave you a little bit of everything. I gave you one where mean value theorem clearly applies because it's a polynomial and it's always continuous and it's always differentiable. Gave you an example of a rational function that had a discontinuity. This one was disqualified from the mean value theorem because of a discontinuity on f. Example 3 was disqualified because it was not differentiable. And how did I know? I took its derivative, and its derivative had a discontinuity. There's a place where the derivative is undefined. And if the derivative is undefined, it's not differentiable. Cool? Clear? I hope we're clearer than mud right now, and I'm not sure we are. In example 4, we were able to set up an interval for that same function that wasn't differentiable so that mean value theorem did apply because we excluded the place on the function where it wasn't differentiable from the interval we cared about. Good? And before the recording started, we talked about infinity, and it was awesome.